are acting like the same circuit, no matter how I build it.
Oh.
It's doing the debouncing thing. Like, I can't do the first one. Like, because I'm trying to compare it to the table where it's like on, off, turns the LED on. Yeah, none of that's matching. Like, some of it's matching up, but like one of them doesn't. And I wonder if it's not supposed to match up, if that's the thing. But
Hold on, I gotta let Bill in.
You can email him.
yeah, I could. But I feel like if I say like, yeah, is this how it's supposed to work? He'll be like, I don't know. Is it supposed to work like that?
I'm really worried for Boris Johnson.
Why?
Boris Johnson.
He's in the hospital.
Oh, he is?
Yeah, and he's pretty young. Like,
who's Boris Johnson?
Prime Minister of
He's the
England.
Prime Minister of...
Oh. Well then.
If you Google him, he looks ridiculous. He looks kind of like an orangutan.
Yeah, he looks like Trump, basically.
What was it? Boris
Johnson. Yeah. What about Prince Charles? Heard anything about him?
No, I haven't.
Ah, yes. Wait, who spelled Boris with one R?
Yeah, one R.
Huh.
Last night, my mom got like 1,000,000 points in Scrabble because she spelled rivet, but neither of us could remember how rivet was spelled. She spelled it R-I-V-O-T. And I was like, yeah, that sounds right. It's E-T.
E.T., yeah.
And rivet isn't a word, but we were both sure it was.
Rivet.
That's why I don't play Scrabble, because one, I suck at vocabulary to begin with, and two, I don't know how to spell anything.
I don't know how to spell anything either. Yeah. One of those things.
Like, if autocorrect was not a thing, I'd be screwed.
Yeah.
I have most of the 2-letter words memorized, so it's a big advantage.
Well, it looks like this will be class today.
Well, we have 4 minutes.
Wait, can y'all hear me?
Yeah, I can hear you.
Oh yeah, okay, yeah.
Where are you now?
Oh, I'm in Richmond right now. I don't get right now.
Hey.
Yeah, you and Kyle.
Woo.
Wait, Kyle, you in Richmond?
Yeah, I'm at my sister's apartment, which is in Richmond.
Even though social distancing, we should meet up. Even though.
Let's see.
No, we can't hear you super well, though.
Yeah, we can't hear you really well. It's very low volume.
How about now?
Better.
Okay, yeah. Yeah, my speaker is just acting super weird.
Oh.
Every single time I lock it. So, yeah.
So whose apartment is that?
Me? Oh yeah, this is my sister's house. So.
Okay, cool.
Wow, that's sounding like the same story
I
from
know.
me.
Yeah.
I'll take your sister.
Well, college kid doesn't have a place to go, so the sister just.
Yeah. What does your sister do, Bill?
She's a diabetes doctor.
Oh, wow. Okay. So she's probably busy too now, right?
Yeah, at the hospital, wearing masks.
One of those essentials.
Yeah.
All these people getting diabetes now.
Eating too much.
Yeah, it's hard because like people now no longer want to go to the hospital anymore for whatever reason.
Yeah.
So she cannot treat her patient, and she still have to treat her patient.
Yeah.
It's weird.
Yeah.
All right, I know we still got like 2 minutes left, but like, where everyone at?
Yeah, I know. Oh, wait, here's Andrew. Got to admit him. Okay. Okay, so Tenzin, Jeff,
Joe.
Yeah. Joe's usually right on. Let me check.
Oh, and then John too.
Oh, and John, yeah. Let me check my email, make sure. Write down. I don't see any emails from them. Panicked emails. Oh, here comes John. Okay.
I mean, we still have a minute.
Yeah. And here's Jeff. We're just waiting on Joe. Where's Joe? And Tenzin. Or Tenzin hasn't been coming that often. Aha! She is. There she is. Okay. Now Joe. Joe, come on, Joe. Don't break our...
Joe.
Come on, we could actually have everybody today. Come on, Joe. Anyone text Joe?
I have no form of contact with Joe.
I do, actually. I have his text.
So how's the outside weather out there, Leif?
Very nice.
Yeah, it's pretty nice.
I'm assuming you're on your back porch.
I am.
If I remember correctly.
It was like a little cold when I first got out here, but it's warming up nicely.
Ah. How long have you been out there?
Like 30 minutes.
Oh, okay.
I think I'm going to, after this, go paint the other porch. Because yesterday I scraped it down so that I could repaint it, and now I can repaint it.
Cool. Just texted Joe. Hopefully he'll come in. We'll give him a minute because might as well. Computer's being dumb, I'll join on the phone is what he said. Okay, so he'll be coming in a second.
Oh, right. We have the vote for the student government stuff sometime soon.
Are those votes out yet? Or are they coming?
Oh, they're coming in. All I can choose is one person for president, and there's only one option. There's nothing else.
Who is it?
Renita.
Kusafa?
Yeah.
Hey, Joe, we can see you.
Yes.
Cool.
Oh, she was in our chemistry lab.
Yeah, I know who she is. I was just like, I know Renita. That's all I knew.
All right, guys.
Wait, no, it's a scroll.
Guys, can you remind me? I'm pretty sure we were finishing a worksheet.
Yeah.
Ampere's Law worksheet, right?
Yeah.
So, and remember, it's going to remind everybody that yes, I take these worksheets from the book's problems, but I want you not to use the solutions. That's just not. I mean, that's for homework where you're going to sit together with solutions and work, through them, right? But if you're just, but here we want you to sort of struggle through, right? That's the point.
Yeah.
This, right? Where you don't just look, because even if you look at the solution and you understand it, it's not as valuable to also, so there's two things, right? There's using the solutions responsibly, like we talked about for homework, and then trying to just struggle through to get a handle on stuff we saw in lecture. Okay? Yeah. So try to just not look at the solutions. I know the problems are not easy, but if you can stop yourself from looking at them during the worksheets, that would be good. And I think everybody, so Leif, you weren't here, but I think it's the Ampere's Law worksheet, right?
Yeah, I'm pulling it up.
Okay, cool. And pretty much people were, I think, almost through the first two parts, right?
Yeah,
okay.
I think so.
Okay.
So, Dr. Shank.
Yeah.
So I tried to do like part 1 and part 2, but do we have like this? I know you say you have a solution, but can we check the answers? So that I know?
Yeah, you can check the answers with me. Yeah.
Okay. Yeah. Because I'm pretty sure I'm not doing it right.
Okay.
So I don't know, like say the first one, does it look like it should?
I really can't see that too well.
Oh my God. Is it dark or what?
Yes, you got the first part right.
Oh, how about the second?
I mean, I can't exactly see the things, but it looks like the right thing to me.
So it is like B is mu naught I over 2 pi.
Yeah. Mm-hmm. So it would be the same as if you had just a wire of current, right?
Yeah.
Yeah.
And then for part B, it's gonna be the inside will be half of mu naught I, mu naught J times A. Would that?
No, for the second for 2.
Yeah, like where J is proportional to S.
S, right. So J, so now you have to integrate, right, to get the current.
Yeah.
So what did you?
So I was trying to integrate JDA from 0 to A because inside the
Yeah.
wires,
Yeah.
right?
Yeah.
And
What do you get for that? What do you get for just that integral?
J pi A square. I mean, I just kind of was not sure what J
Well,
is.
okay, so you have, think about the dA for this, right?
Just like the area of the one in the loop. Like say a 2 amperian loop inside the wire, so it's just gonna be the area of like a circle. Right?
Well, okay, so think about what you're going to use for dA is going to be in, like cylindrical polar coordinates.
Oh.
Yeah.
Okay. Okay, that makes sense. Let me try again.
Hey, Shank.
Yeah.
So when I'm doing this integral, I have it so that I have b times the integral of ds or dl, whatever. You know what I mean?
Integral b dot dl?
Yeah, so I have b dot dl.
Then you pull the b out.
Pull the b out.
Good, yeah.
And I know that's gonna work out to be the integral of ds is gonna be like 2 pi r, right? Because that's just, the loopy thing around the outside.
Mm-hmm.
Is it specifically 2 pi dr and then I just integrate it? Or is it, what's the formalism there?
Okay, so no, but so you're just trying to figure out what the length of the loop is. So you're not really, I mean, you could integrate it, right? You could be like, my dl is, 2 pi dr, then r goes from 0 to s.
Okay.
But it's just like when you do like Gauss's law and you have like E dot dA and the E comes out and you're like, dA, what's the area of the surface area?
It's just going to work out to be 2 pi r.
It's going to work out to be 2 pi s, whatever, yeah.
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 I have another question.
Mm-hmm.
So when it says that J is proportional to S, does that mean that, we're assuming it's proportional just with a constant.
Yeah.
So I can just write that J equals KS, and then kind of just, would I have to do an integral to find the current? Okay. And would that integral be the surface area of the outside of the cylinder?
Right, but you're integrating from along S, right?
Right, okay.
Does that make sense to you?
I might check back in a second to make sure I have set it up right. But... And the thing coming out of the integral with J in it and whatever is going to be the current, right?
Yep, that's what you're after. So it's the integral J dot dA, right? That is the current. It's the current that's piercing that area dA, right? That's the idea.
Okay, so that area, if it's the current piercing that area, it seems like it should be pi r squared because it's moving through the wire.
Right, but you remember, so if you had nothing, if the current was not dependent on S,
Yeah.
Right? Then you could just be like, oh yeah, it's just, you know, the integral of 2 pi s ds, which of course integrates 2 pi s squared.
Over
Right?
2. Yeah.
Nope, 2 pi s ds
Oh,
integrates
right.
2
Yep.
pi s squared. Got it? But that's not true, right?
Yep.
J depends on s.
Mm-hmm. So it would just be 2 pi s then.
No. So think about what you have to do. It's the integral j dot dA.
Yep.
Okay. So dA in this case, like dA in this in general for this the area we're talking about is the, you know, the area of a circle, right? Because the wire is circular, etc. Right? And the current is piercing through the wire. But you have to add up all the current from all the different s's because J depends on s.
Right. Okay.
Right? So you have now the dA, right, is just the usual dA for cylindrical polar, which is 2 pi s ds. Or you can think of it if you like. Sorry, I should say more concretely. It's s ds d phi, but phi goes from 0 to 2 pi, so you might as well just call that 2 pi. But it's s ds d phi, right? And phi goes from 0 to 2 pi, so we can just replace that. But just to be very clear about it, it's s ds d phi.
All right.
Right? And then you gotta put the j in there that you know, right?
Yeah.
Okay.
Shank, is this right for the answer for the current? Can I just tell you?
Oh, sure.
2/3 pi ka cubed.
Yes, indeed.
Cool. So I still need to do the calculation though. Like I just found the current. I still need to do the. Yeah.
Indeed.
For those Shane, does it look like what it is for B?
Yeah.
Okay.
You can put it in terms of current, right?
Yeah.
If you want.
Like,
Right.
oh yeah, true. You're right. You are I. Yeah. Maybe that's look better.
By the way, on the third problem, does the slab extend to infinity in the x and y direction?
Yeah. So yeah, so if you yeah, just don't pretend you're not close to the edges. That's
Okay.
the way to do it.
Shank,
Yeah.
for the magnetic field for part 2,
Mm-hmm.
is it mu naught a squared over 3?
Mu naught a squared. I don't think I even wrote that down. Let's see. So it's going to depend on S, right?
So I just did the integral from 0 to a, which was the radius of the wire.
Yeah, but what about for S less than A?
Then it's just not that a. It's just s instead of a.
Okay,
Right.
so what do you get in that case?
Mu naught k s squared over 3?
Yes, over 3. I have 3, yeah. Good. Yep.
Cool.
Yeah. So is everybody done with 1 and 2 or still working on 1 and 2?
Yeah, I'm done with 1 and 2.
Okay, cool. Good.
I'm on 3.
All right. What about you guys that I can't see? John and Tenzin and Jeff and Scales.
I'm working on 3 right now.
Okay, good.
I'm finishing up 3.
Good. John and Tenzin?
Got 1 and 2 and working on 3.
Yeah, I'm on 3 as well.
Okay, everybody's on 3. So let me know when you get the direction of the B field. Remember we talked about how to do that with current? Like putting your thumb in the direction of the current and your fingers curl in the direction of B, right?
Mm-hmm.
The closed hand, right hand rule. Closed right hand rule, I mean.
I'm kind of confused on how to start with this problem, honestly.
Okay. All right. Well,
So-
the first thing you should always do when you're doing something like this is figure out what is the direction of B that would help you. It would help you figure out what kind of loop to use. Right.
Right. So the direction of B is through the slab, so it would be direction. The loop is curling, right?
Oh, you mean the direction of the current?
Yeah.
Okay. Okay. So imagine the slab is like coming.
So let's say it's
like
my
this.
switch.
There you go.
Then, since current's moving this way,
Yes.
then it would be curling
Yes.
this way along the switch.
Yeah. Exactly. Yeah. So basically, right, but don't think of it as a circle, right? Think of it like right?
It'll be the
slab.
center.
Yeah, it's like a rectangle basically, right? Because the slab is rectangular, not like a wire.
Yeah.
So what kind of loop do you think you should make? What should it look like? A circle?
I mean, it should look like just a rectangle, but like square down.
Yeah, right. Because you want to know what's inside, right? Yeah. So I guess you're doing the inside first.
Yeah.
So think about the direction of B, and is it different for positive or negative Z?
I mean, because you said so, it seems like it should be, but I don't know why.
Well, okay, so imagine now the slab is like here's my iPhone, right? So here's the slab, and I'm thinking of the current coming this way towards me. It's easier because of my hand. All right. So let's say that right in the middle, see where that pop socket is?
Oh.
That's the 0.
Mm-hmm.
0. So if I put my hand in the direction of current, I'm going to be like this.
Mm-hmm.
But then as I turn around, keep going, it's going to be like that, right? On the underneath the pop socket.
So you mean it's going to be going a different direction?
Yeah.
Yeah.
So like it's going to go like this on the top.
Mm-hmm.
And as I curl my hand around to go to the bottom part, it's going to go like that. Right?
That won't affect the magnitude, but it will affect the direction, right?
Right. So, but it helps you because you can, it tells you where B is 0. B has to be 0 at a certain somewhere, right?
Okay. So in the center.
Yes.
Yeah. So am I breaking up this? So if I'm taking an integral of this, do I have to break it up into 4 parts, or maybe like 2 parts?
Yeah, I mean, yes, of course you do. But if you've put your Amperian loop in a particular place, right, you can, which is the reason for determining if the B field 0 somewhere, right? If you make the Amperian loop so that one of its legs is on that 0 line, then you don't have to worry about that leg.
Okay.
And then you have only 3 legs to worry about.
Yeah, sure.
Yeah. Guys, I'll be right back.
All right.
Hey, Dr. Shank. I think I may be getting somewhere with part 3.
Okay.
So I did the B.dA integral. I got B is equal to mu naught Q enclosed over L.
You got what?
Mu naught times Q enclosed over L. Is
I'm
that?
sorry. You said B. You said you did B.dl.
Yes.
Yeah. Okay. And what did you get for that? Mu naught I enclosed. Oh, yeah, over L. Sure. Yeah. Now you got to figure out what the I enclosed is, right?
Okay. All right.
Yeah.
Let me
Good.
get back to
Yeah.
with them in a minute.
Yep.
I think I'm done with number 3.
I think I might be as well.
Okay.
I don't know. You want to go first, Leif, or?
No, you can.
Okay, give me a second. All right, so it'll be this for Z in the slab. This little bit right here, mu naught J Z
What do I
Y
have?
hat
Yeah,
minus
yeah, J.
Z. That's a Z. Yeah,
Yep.
and then I go down, and then this is what it's like outside of the slab.
Okay.
All right,
Yeah.
cool. And then, yep,
Okay.
there we go.
Leif?
Yeah, I have the same thing as Joe.
Okay.
It's this is for Z greater than A, this is for Z between, and this is for Z less.
Okay.
It agrees with Joe.
Yeah, good. Okay. Getting how to use Amperian loops, I hope.
It's like worse Gaussian surfaces.
Yeah, it is. I agree. Yeah. Okay,
I
let's
think Ampere was just like, hey. And Maxwell was like, yeah, it's fine. Neither of you did anything important. I grouped them together.
That's right. That's right. Let's just take another 5 minutes or so, see if everyone can get there.
Shank, have you ever heard of XKCD?
Yeah, of course.
Have you ever heard his song about every major's terrible?
No, I have not. That sounds amazing.
It's set to the tune of Modern Major General, you know.
Yeah. I know.
The one that are relevant to us is astronomers cringe when they hear supermoon or zodiac. And for physics, it's while majoring in physics seems to promise you a Richard Feynman-like career, the wiki page for physics major redirects to engineer.
That's true.
Oh my god.
That's fantastic.
Rip.
That's very awesome.
Mm-hmm.
Okay, two more minutes or so. Do you want me to go over number 3?
Yes, but I have a question first.
Yeah. Mm-hmm.
So when you say like you set the loop to one side of the loop where the B field equals 0, like how did that really like turn out? Like I just don't get the idea of that.
So the idea is that you have hold on, let me share my screen. I might as well now. Hold on just a second. And we are recording. I remembered. So the idea is that you have like, so if you have the slab, hold on, it's not working. So if you have the slab like this, right? And this is the z-axis. This is the y-axis, let's say. The current comes out like that. That you know that that on when z equals 0, so on the y-axis, the B field is 0, right? Because the B field points. If you go like this, it points in the negative direction, right? So the B field goes like this: negative direction here,
Yeah.
direction here,
Yeah.
right? And so it's got to change. It's got to change sign right here. So that means it's got to be 0.
Okay. Okay.
So I mean, if you can put your loop like this.
Oh.
Then one of those sides you don't have to use.
Yeah, true. Oh, so it's just gonna be like go to the negative y direction, right? Because because the other side can cancel out too. Can it? Like,
well, no. So it's just that when you think about the b.dl integral, right?
Yeah.
Around the loop, it has to be. So that's going to be like integral b along top, right?
Yeah.
Plus, all right, you've got to put the dot product in still because think about the signs, but and then side 1, let's say here, side 1 b.dl plus integral bottom, right?
Yeah.
Plus the integral side 2. Yeah?
Yeah.
All right. So in the bottom one, b is 0, right?
Yeah. So that can goes away.
Right. What about these?
Right. I mean, 1 and 2 would cancel out too because they have different directions.
Cancel or what? What happens to the dot product?
Oh. How? I don't know.
So what is the direction of b on this side here?
That's gonna be downward, like negative z.
No, we already determined what the direction of b was for this entire top part.
Oh, so it's negative y.
Yeah, so it's negative y, and what is the direction of dl along the side?
0, so 0.
Well, the direction is
sum to 0.
So dl is, what is the direction of dl?
Direction of dl is gonna be negative y as well?
No. Along this side.
I thought there's no dl, not dy. DL.
Yeah, dl.
Would that be just, would it be dz?
Would be what?
Like dz because
I'm just asking about the direction.
It's going to be downward. Like
downward, right.
Yeah.
So you've got B field looks like this. And DL looks like this.
Yeah. Oh.
It's a dot product.
So 0.
Yeah. Same on this side, yeah?
Oh, that's how it's 0. Okay.
Yeah. Make sense?
Yeah. Okay. Oh, okay. Now I get it.
Okay. Good. So we should probably just stop working on the worksheet up ourselves and look at, we were just looking at this, right? Might as well keep going. So the Amperian loop is this guy, right? Where that's our Amperian loop. And the next thing we have to do is just think about the I enclosed, right? Okay, and that's the integral J dot dA, right? Where dA is that vector normal to the surface bounded by your loop, right? So you've got a loop up here, and the surface is bound. This is the surface here, right? That's bounding that loop, yeah.
Mm-hmm.
Okay, so so that means that what is this then? What is dA going to be? Or actually, why don't we just do the dot product? Is the dot product, can I just get rid of the dot product? Like, what is the direction of J? What's the direction of dA?
Well, they're both in the X direction, so.
They're both the X direction, right? Which is coming out of the board, right? Because think of right-hand rule. I'm going around my Amperian loop like this, and the thumb is pointing out of the board, which is our X direction, right? So X.
They could vary with a minus sign, but that wouldn't matter, right?
Yeah, and it's usually convention to do the right-hand rule. You know what I mean? To say like, oh, I'm the direction of integration. You use right-hand rule to figure out that's the direction of the normal, right? Sorry, that's the conventional direction of the normal. Because you're right, it could also be going in, right? Because it's not a closed surface, so there's no definition of outside or inside, right? For Gaussian surfaces, we know that we always choose the outward pointing normal. That's easy because it's closed surface has an inside, has an outside. Here's it does not. But the convention is you when you're going around your loop, you're integrating around your loop, right? DL. That direction is your fingers, and then your thumb points in the direction of the out of the conventional normal. Does that make sense?
Yep.
Yeah.
Okay. So that means they're both in the x hat direction. So we have, dA is equal to just dA magnitude x hat. And of course, J we already know is just some constant x hat. So that means I can get rid of the dot product. So it's just J dA. And J is a constant, right?
Mm-hmm.
J integral dA. And I can integrate dA, just be like, yeah, well, that's just A, whatever A is. What's A for us?
dy dz.
Well, no, I already integrated it.
Just be yz.
Yeah, so it's well, think of it, it's your loop, right? Your loop has a certain size. Just like in Gaussian loops, they have a certain size. Right now we're inside.
I just made mine L.
Yeah.
L long.
Yeah. Right? That's L long, whatever, right? So what is the area?
ZL.
Yep. Yep. Right? So that is the I enclosed. Make sense?
Yep.
Oh.
Okay.
And then this guy here, this is the only one that survives up here, right? So you have integral B dot dl on that top part of the Amperian loop is going to be that mu 0 j l z. Yeah. And then what is this here?
Just B and L.
Yeah, it's just it's just BL because you're gonna the dot product because they're both B is in this direction here.
Yeah.
And then so here's B again, and then along the top of the loop, that's DL is also here, right? So this is DL, this is B. So the dot product, don't become a minus sign, anything. You just get BDL, and then I know it's constant along that area, so I can go BDL like this, right? Mm-hmm. And of course, that's just BL. Right? Okay. So that means that B is just mu 0. Oh, I forgot the L. Mu 0 J Z, right? And then you have to say like, what is the direction, right? So inside the slab, if z is negative, so let's write down the direction now, okay? So right now it's y hat, right?
Yeah.
I think that's right? So we get, oh, no, so we have to put a minus sign, right?
Yeah.
Because minus y hat.
Yeah.
But then when j changes sign, that'll cancel out that negative sign, and you'll get plus y hat, right? When j goes to negative, z changes sign. When z changes sign, right? Going to the bottom here, right?
Yeah.
And so you get that. This is inside. Yeah?
Yep.
Okay. And now what happens when z is, when we're outside of the slab? Remember the slab is like
Yeah. Then your I enclosed would just be J L A.
Yep. Your I enclosed becomes so outside. You're enclosing all the current, right? So basically it's I enclosed is equal to mu 0, J L A. Yeah. You've got all of the current that you can in that Amperian loop, right? And so therefore the same thing happens here, right? Because the B field is going to be in the same direction. It's not changing direction, right? And so you're going to have the same idea. You're going to have B is equal to mu 0 JA, where the L's are going to cancel again, right? I'm not going through that, right? Y hat. And then we do have to say something here. We have to be like, oh, it's going to be in the negative y hat direction when your z is greater than a. And it's going to be in the positive y hat direction when z is less than minus a, right? That's right. That's the way to say, isn't it?
Yeah.
Yeah?
Mm-hmm.
Z. That's supposed to be a z. Okay. All right, everybody get that? So that problem is, not the hardest, but it's hard to wrap your head around it first. Okay. All right. So I encourage you to go look at other problems with Ampere's law. Okay.
All right.
And we'll continue on Wednesday. And I will, I haven't graded your exam corrections, but I'm going to do that before Wednesday.
Okay.
Okay, guys. Well, we'll see some of you in quantum and some of you in MATLAB.
Bye.
So, bro.
And some of you will never see again.
Let's hope that's not true.
Cough, cough.
Right.